Corrosion does not explode. It does not make noise. It does not cause instant failure. And yet it destroys infrastructure worth trillions every year, weakening bridges, pipelines, ships, vehicles, and industrial systems from the inside. Corrosion is one of the most destructive processes in engineering, not because it is violent, but because it is quiet, constant, and unavoidable. Most people associate corrosion with rust, the familiar reddish-brown layer on steel. But rust is only a visible symptom, not the real cause. Corrosion is not a cosmetic issue. It is a fundamental electrochemical process in which metal slowly breaks down at the atomic level. Once it starts, it cannot be turned off. It can only be slowed, redirected, or controlled. The key idea to understand from the beginning is this: metals are not naturally stable in their refined form. Iron, aluminum, and copper originally existed in nature as ores, mostly oxides or sulfides. Extracting pure metal required enormous amounts of energy. Corrosion is simply the metal's tendency to return to a lower energy, more stable chemical state. If you like similar educational content, please like, subscribe, and share the video with your friends. In other words, metal wants to corrode. Not because it is defective, but because physics and chemistry favor that outcome. The moment metal is exposed to an environment that allows this process, corrosion begins automatically. Corrosion does not require immersion in water. Humidity from the air, oxygen, and a small number of ions are enough. That is why cars corrode in garages, structures degrade indoors, and metal components fail even in seemingly dry environments. Extreme conditions are not necessary. Ordinary surroundings are sufficient. The true engine of corrosion is electrochemistry. On a metal surface, microscopic regions form that behave like tiny electrical cells. In one area, oxidation occurs. In another, reduction takes place. Electrons move, ions migrate, and metal atoms slowly leave the solid structure. The process is so subtle that it remains invisible until the damage becomes serious. This is what makes corrosion so dangerous. It does not destroy materials all at once. It weakens them internally, often in places that cannot be seen. By the time corrosion becomes visible on the surface, structural integrity may already be compromised. In this video, we will explain without simplification how corrosion truly forms, what happens at the atomic level, why water, oxygen, and salts matter, why some metals corrode faster than others, and why rust is not the same as corrosion. Once you understand the mechanism, you will never look at metal structures the same way again. When we zoom in on metal at the microscopic level, the idea of a perfectly uniform, solid surface quickly disappears. In reality, every metal contains tiny imperfections, impurities, grain boundaries, internal stresses, and structural variations. These differences are invisible to the naked eye, but they are more than enough to trigger corrosion. The moment metal comes into contact with moisture and oxygen, its surface begins to act as an electrochemical system. Certain areas become anodes, while others turn into cathodes. Between these regions, electrons start to flow. Without wires, without external power, the metal effectively becomes its own microscopic battery. At the anodic sites, oxidation occurs. Metal atoms lose electrons and dissolve into the surrounding environment as positively charged ions. This is the critical moment where real damage happens. Material is physically removed from the structure. The metal is no longer solid at that location. It has been transformed into ions. At the cathodic sites, the electrons released at the anode are consumed. Most commonly, they participate in reactions involving oxygen and water, forming hydroxide ions. Together, these anodic and cathodic reactions create a closed electrochemical loop. As long as this loop exists, corrosion continues. What makes this process especially dangerous is that no external energy source is required. Everything needed for corrosion is already present. Potential differences within the metal, oxygen from the environment, and a thin layer of moisture acting as an electrolyte. Once the circuit is closed, corrosion becomes self-sustaining. Water plays a much more important role than simply being wet. It acts as an electrolyte, allowing ions to move between anodic and cathodic regions. The more conductive this electrolyte is, the faster corrosion proceeds. That is why dissolved salts dramatically accelerate corrosion. Seawater, road salt, and industrial atmospheres create extremely aggressive conditions for metals. Another crucial aspect is that corrosion never starts evenly. A tiny scratch, a weld, residual stress, a compositional difference, or contact with another metal can create a local anodic region. Once this happens, corrosion concentrates in that area. While electrons travel through the entire metal component, the actual material loss becomes highly localized. This is why corrosion is so deceptive. From the outside, a component may appear strong and intact. Internally, however, its structure may already be seriously compromised. Small anodic regions can remove large amounts of material, while the rest of the surface remains relatively unaffected. The electrochemical mechanism of corrosion applies to nearly all metals. The differences lie in reaction speed and corrosion products, not in the underlying principle. Iron forms rust, aluminum forms a thin oxide layer, copper develops a patina, but in every case, electrons flow, ions migrate, and metal seeks a lower energy state. This also explains why corrosion is so difficult to stop. Removing rust alone does nothing. To truly control corrosion, the electrochemical circuit must be interrupted by isolating the metal from the electrolyte, altering electrical potentials, or forcing reactions to occur elsewhere. Once the electrochemical nature of corrosion is understood, a critical realization follows. Corrosion is not a single process with a single outcome. It appears in multiple forms, and the most dangerous ones are often the least visible. Rust spreading evenly across a surface is usually not the real threat. The real danger lies in corrosion that attacks selectively, locally, and silently. The simplest form is uniform corrosion. Here, material loss occurs relatively evenly over the entire exposed surface. Thickness gradually decreases, strength is slowly reduced, and the damage is generally predictable. From an engineering perspective, this is the least dangerous type because it can be anticipated, measured, and accounted for in design. Regular inspections usually reveal the problem early. The real risk begins with localized corrosion, especially pitting corrosion. In this case, the surface may look almost untouched, while tiny pits form at specific locations. These pits act as highly active anodic sites. Corrosion proceeds rapidly downward rather than outward, drilling deep into the metal. A pipe, tank, or structural element can fail suddenly, even though 99% of its surface appears intact. Closely related is crevice corrosion. This form develops in narrow gaps, under gaskets, bolts, lap joints, washers, or overlapping plates. Inside these crevices, oxygen becomes depleted, while ion concentration increases. This creates a strong electrochemical imbalance between the crevice interior and the surrounding surface. The result is intense, highly localized corrosion that remains hidden until structural damage is severe. Another major threat is galvanic corrosion. This occurs when two different metals are electrically connected and exposed to an electrolyte. Together, they form a galvanic cell. The less noble metal becomes the anode and corrodes much faster than it would on its own. The more noble metal is protected at the expense of the other. Poor material selection, such as directly joining steel and aluminum without insulation, can turn an otherwise solid design into a corrosion failure waiting to happen. One of the most dangerous forms is stress corrosion cracking. Here, corrosion interacts with mechanical stress. Even relatively low tensile stress, combined with a specific corrosive environment, can initiate microscopic cracks. These cracks propagate rapidly, often without visible plastic deformation. Components can fracture suddenly and catastrophically, with no clear warning signs. There is also intergranular corrosion, which attacks the boundaries between grains in a metal's microstructure. From the outside, the metal may look normal. Internally, however, cohesion between grains is destroyed. The material loses strength and toughness, becoming brittle and unreliable. This type of corrosion is often linked to improper heat treatment or alloy composition. What all these forms have in common is selectivity. Corrosion always seeks the weakest point. Whether it is a geometric feature, a metallurgical defect, a chemical imbalance, or a design flaw. It does not spread randomly. Once a vulnerable area is found, corrosion focuses there with maximum intensity. This is why corrosion is such a serious engineering challenge. It can remain undetected for years, quietly progressing beneath the surface until a structure fails suddenly and without obvious cause. Many catastrophic failures are later traced back to small, localized corrosion mechanisms that went unnoticed. At this stage, one question becomes unavoidable. If corrosion is natural, electrochemical, and unavoidable, how can it be controlled at all? Once corrosion is understood as a natural electrochemical process driving metal toward a lower energy state, one conclusion becomes unavoidable. Corrosion cannot be completely eliminated. It can only be slowed, controlled, or redirected. All corrosion protection strategies are essentially attempts to break or interfere with the electrochemical circuit that enables corrosion. The most straightforward approach is to isolate metal from its environment. If contact with water, oxygen, or an electrolyte is prevented, corrosion slows dramatically. This is why protective coatings are widely used. Paints, varnishes, enamels, and polymer layers act as physical barriers. Their weakness is durability. Even microscopic damage can create ideal conditions for localized corrosion, sometimes accelerating degradation beneath the coating. More effective in many cases are metallic coatings, particularly zinc coatings on steel. Zinc is less noble than iron, meaning it preferentially oxidizes. In this system, zinc sacrifices itself to protect the steel underneath. Even if the coating is scratched, zinc continues to corrode instead of iron, providing protection as long as zinc remains. This principle is also used in sacrificial anode systems. These anodes are intentionally attached to ships, pipelines, storage tanks, bridges, and offshore structures. Made from metals that corrode more easily, sacrificial anodes become the preferred anodic sites. The protected structure becomes the cathode and remains intact. Once the anode is consumed, it must be replaced. Protection is always temporary, never permanent. A more advanced solution is impressed current cathodic protection. In this method, an external power source forces the protected metal to remain cathodic. Anodic reactions are effectively suppressed. This technique is highly effective and widely used for large-scale infrastructure, but it requires continuous monitoring, precise control, and a constant energy supply. Another important mechanism is passivation. Some metals, such as aluminum and stainless steel, naturally form extremely thin but stable oxide layers on their surfaces. These layers isolate the metal from the environment and significantly slow corrosion. However, in aggressive conditions or when the passive layer is locally damaged, corrosion can restart, often rapidly and in a highly localized form. Design plays a crucial role as well. Sharp corners, crevices, water-trapping geometries, and direct contact between dissimilar metals all promote corrosion. Good engineering design can dramatically extend service life even without advanced coatings. Poor design can defeat even the best protective systems. Ultimately, corrosion is not just a material problem. It is the result of chemistry, physics, environment, and human decisions interacting over time. Metals do not corrode because they are flawed. They corrode because conditions allow them to return to a more stable state. Corrosion is silent, persistent, and unavoidable. It cannot be defeated, but it can be understood. And understanding corrosion is the difference between a structure that lasts 10 years and one that lasts a century. Rust is only the final symptom. Real corrosion begins much earlier, at the atomic level.